As you know, the Science Club's been hosting science lectures continuously, except for a brief 2-year gap there during COVID, but for 12 years. First one was back in 2012, when at the time it was called the Library Seminar Series. It was done in the mornings, and it was at the library. The first one was Bob Collins talking about human memory, which he's done a number of times. So after 10 years of these lectures, what we now know as the Frontiers of Science series stands out, alongside many of the other cultural opportunities that we have here in Sisters, opportunities to hear music, to go to the quilt show, the art galleries, the farmers market, community theater, and all the other things. But I gotta say, the Frontiers of Science for 10 years has been the only place for science nerds like ourselves to get the incentive to come out of our house on a cold Tuesday night in winter. So we thank you for all that. Now, the astute observer would note that it is neither a Tuesday night, nor is it winter, nor certainly is it cold outside. But as we continue to learn, that small minority of science nerds here in Sisters really isn't such a small minority after all. We've got now, as a science club, something like 500 names in the email directory, and I hope you all are in it. If you're not, you can certainly sign up over at the table there. And I think at the Belfry for the Tuesday nights, we've typically had something like 150 or 200 people per night for these lectures. So that's a tribute to all of you for coming, and also to the organizers of these events for coming up with a great series of speakers. We also have been getting a lot of good ideas for additional talks, and one of the things that we've also heard is some demand for, year-round. And so this summer, with the new leadership led by David Durham and the largely new board, we're trying out a few new tricks. One of them is exploring response to these science talks during the summer. And so, David, you had a couple quick questions you wanted to ask.
Yeah, how many of you heard about this because of the nugget somehow? Because of the nugget.
Nugget. And email.
And then how many from email? And how many because they're in the Astronomy Club, which is also our our guest, co-sponsors for this talk tonight.
How many of you thought we were here for fire prevention? So, the other thing we're trying is setting up these talks in conjunction. The Science Club is not the only science club in the area. So, as we can tell tonight, we're doing something in the Astronomy Club, but leveraging that email constituency and our outreach and through social media and relationship with the Nugget, etc., we are now promoting a number of other sort of co-hosting and cross-promoting things. So recently we've done a couple lectures at the Pine Meadow Ranch and Center for Arts and Agriculture. So a couple recent ones were environmental impacts of the Oregon lifestyle. Another one, gardens and how that affects insect conservation. And coming up on August 15th is one on art and science involving glaciers. And those are going on at Pine Meadow Ranch. We also worked earlier this month. It was earlier this month with the Central Oregon Geoscience Society, who is one of whom I think the co-founder presented to our group at the last lecture. But they had a student talking about basaltic andesites, which we now know is the dominant lava type here in Central Oregon, of course, for those of you who are there. And of course, the Science Club is very proud to co-host the talk tonight alongside the Sisters Astronomy Club. And however this all goes, we will be picking up the Frontiers in Science starting in September, the fourth Tuesday every month, starting in September, with Dr. Donna Davis from the U of O, who was rescheduled from last February. And that's gonna, I think we've all been looking forward to that one for a long time, talking about augmented reality, virtual reality, extended reality, artificial intelligence, sort of roll your own reality. It should be a really good talk, so we're looking forward to that. And of course, like all of you, I'm certainly looking forward to what Dr. Larson has to share with us tonight. Personally, I'm also grateful for the fact that the Science Club and the Astronomy Club continue to work together. I mentioned the Science Club's been around for some 12 or 13 years now, but as a former teacher at the high school teaching physics and chemistry and the engineering classes, and as one of the early members of the Science Club since its inception, I've definitely seen the impact that the Science Club has had on our students in the classroom and outside our classroom. And I've also had an opportunity to see what the Astronomy Club has done for us, both in and outside the classroom. So I'd like to just, as a member of the Science Club, I'd like to give a shout out and perhaps a round of applause for some of the Astronomy Club members that have really been, and I gotta say, with the, starting out with the indefatigable Ron Thorkelson, who's in the classrooms every week, and along with Jim Hammond and Rod Moorhead and some of the other members, Lynn Carroll, who've been involved with STARS Over the Sisters program, getting our students and our teachers involved, creating an Astronomy Club, getting students writing about astronomy in the Nugget. Let's give them a round of applause.
Thank you.
And I'm going to shut up really soon here, but lastly, I'd like to thank you. I'd like to thank for the Sister Science Club, the people that make this happen. As I mentioned, David Durham, whose idea this was, and some of the other board members who are here tonight, this concept of having summer lectures is new, and we're trying it out. It's great to have new people trying out new things. And especially on the board is Gail Todd, who I don't know where she went right now, but Gail, who consistently sets up so many of the logistics and details. So please, how about we thank the board. And now I'd like to invite Jim Hammond of the Astronomy Club to, who will introduce Dr. Larson.
Okay, thank you, Rob. Let's hear it for the Science Club, too. Can we get your email list?
There's a price on everything.
Our email list is about 50. But anyway, I'd love to see this kind of a turnout. I am going to proceed to a few slides as you've already seen. This slide is just one I made up for this particular lecture, and it connects to the lecture because 35 years ago, next year, the Hubble Space Telescope was launched. So that's at one end of what Shane is going to talk to us tonight about. This is just a brief statement of our Astronomy Club mission and how we were founded. We were founded about the same time. I think we were in existence when the Science Club started, and but it was almost coterminous in time. And we participated in several science fairs that the Science Club put on. They were really great. And if you wanted to get back to anything, now that we're out of COVID, I think the science fair was a great thing to do, and if you could do that, that'd be great. So there's only one activity that I'm going to kind of tout. It actually takes place out of Pine Meadow Ranch, in the longer name of it, whatever it is, which Rob remembered. We're having tentatively a star party on Friday night. They're limited in the space and the number of people they can have come in. Although they have a big meeting room, they told me that it's because of, I don't know, something to do with their deal with the state, or I don't know, feds. Maybe they're under, maybe they're being looked at by the tax people, I don't know. So Friday night, we're going to start at 9 p.m. And if you have to go on and register on Eventbrite. And this particular slide shows that little tiny URL. And it's actually that and information about the activities that we have planned are in our trifold brochures, whatever you want to call them over there. So please take one of those, say per couple, per family, because I think I only got 60 this time, so I think we're more than 60 today. That's pretty great. And if you register, which the folks who are bringing telescopes will get contacted by me, and I have seveal people. If you are a person who would like to bring a telescope, then tell me about it. And I will inform people who are bringing telescopes. If we cancel, it'll be on Thursday afternoon, Thursday 5 o'clock or 4 o'clock, something like that. So I have a little list of thank yous there. Gratitude to everybody, including all the members of the clubs. And well, we'll see why some of those appear there as I get to after what I do after the talk. You know, fine parting gift and all. You know, you guys can just guess. You could read this while I jabber. Shane and I met first, person to person in 2019 when I invited him here to give a talk, and he gave it at the library. But he was put in contact. I was put in contact with him through a mutual friend, who it turns out I met in 1966 at Wesleyan University. Well, I was a graduate student, and this fellow, Tuck Stebbins, was an undergraduate. So you go back, I don't know how many years, it's like an enormous number of years.
More than we can count, Jim.
And then I believe, Tuck, I was talking to Tuck the other day, and he said he had a phone call when when Tuck was working at Gilla, which is a place where I started my PhD research. He was talking to Tuck Stebbins, who was working on LIGO, the Laser Interferometer Gravitational Wave Observatory. And at that time, I'm not sure how far the gleam beyond a gleam in an eye was LISA, which we're going to hear about tonight. But so there you go, 1984 to now. So, you know, Shane kind of splits up the time that I've known Tuck. And Tuck is a great friend of mine. He told me about, I said, you know any funny stories about Shane?
Uh-oh.
Well, he told me, he said, well, you know, it's kind of funny, but people who don't worry about physics and stuff wouldn't care about whether you have pi in the wrong place or not there in the formula you were calling about, so I'm not going to tell about that. But Tuck started telling me about the number of hobbies that Shane has. So now I hope you can all read that. Shane builds telescopes, and this picture shows 2, but Tuck told me you have a 3rd.
Yeah, my 3rd one's in my
You have one for your daughter, one for your wife, and one for you. And yours is the middle-sized one.
That's
the big one, right? So he builds telescopes, and he calls himself on what do you call it? On X or whatever the hell it's called.
Science Jedi.
A pen nerd. So he's a pen nerd, and I consider myself a pen nerd in the sense that I always carry and I always use, but I don't do a lot of writing except in crossword puzzles, a fountain pen in my pocket. But I have a very small collection, and I wouldn't need anything like that fountain pen. At any rate, he's the kind of guy, and I'm going to turn you over to him in just a second. He's the kind of guy that if you're at a party and there's just too many people, they're all crowded around, it's too busy and everything, you can go over to him. Now, you don't have to know about any of these things, but if you start talking about fountain pens, or telescope building, or probably even sandwich making, the area will kind of clear out. And you can just talk to Shane. That's the beauty of these hobbies. Now, I'm going to turn it over to Shane, and thank you very much, Shane, for coming.
Thank you.
Again, up here to wonderful sisters.
Okay, can you hear me on the mic?
Yeah.
Okay, let me plug my laptop in. I forgot my charger, so I've been laying it in rest so it doesn't run out in the middle of all of this. We will rock and roll. Yeah, baby, look at that. Okay, it's like we know what we're doing. So. Okay. Maybe. Yeah, there we go. Okay. So thank you everyone for coming. Certainly thank you to Jim for the invitation and the Science Club for co-hosting. I do a lot of this sort of stuff. I do a lot of public lectures. I've been to Bend several times. I've visited the Sisters folks. I talk at Worthy Brewing now and then. I talk down at Sun River. I'll be at Sun River tomorrow night. I'm going to talk about the aurora. So I'm from Eastern Oregon. My dad lives in La Grande, which is where I went to high school. I'm an Oregon State grad. Any Beavers in the room? Yeah, a few of you. Okay, yeah, go Beavs. Okay, so Oregon's kind of home, and so I come every summer. I go to Oregon, Washington, and do stuff like this. I was looking at my records. This is my 301st public lecture. Okay, so yeah. So I love doing this. It's very near and dear to my heart to be able to go out and talk to people who are interested in the things that we like. And so it's always a very special treat to talk to people about what we do as professional astronomers. Because the sisters folks, the Astronomy Club invited me, I will talk a little bit tonight about amateur astronomy as well, because it has a role to play in some of the story that I'm going to tell you. But I have to apologize to you in advance, because I am both a professional and an amateur astronomer, which means half the time I'm going to say we, and mean we the professional astronomers, and the other half of the time I'm going to say we, and mean we the amateur astronomers. And it's going to be confusing for you. So you can just figure out which one I mean. I'm sorry about that, but I do both, and I kind of think of myself depending on whichever one it is. Okay, so we'll talk a little bit about both pro and amateur astronomy today. My email address is right there, s.larson. There's a period there. It kind of looks like a star. Don't forget it. At northwestern.edu. I don't know why this is glitching like that, but I hope that's not too annoying. We'll certainly take questions at the end. If there are questions burning in the middle, I'll take them, but I'll kind of control you to keep you from running off and keeping us here until 10 p.m. But what always happens is 2 weeks from now, in the middle of the night, you'll wake up, and there'll be some question you wished you had asked me. And most of you know at this point, and if you don't, your significant other does not want to talk about astrophysics at 2 in the morning. Okay, so that's why my email address is there. You can email me. I'll do my best to give you something to read, point you to a YouTube video or something like that. Okay? Rightscience.wordpress.com, that's my blog. I write there about all kinds of astronomy stuff. Sometimes it's black holes, sometimes it's SETI, sometimes it's lives of stars, all kinds of stuff. It's there so my mom knows what I do, so it's kind of public facing. So hopefully you can find some stuff there that you like. Okay? So, I am the Associate Director of Sierra, which is the Center for Interdisciplinary Astrophysics at Northwestern. One of the threads tonight is that the story of modern astronomy is so complicated that it can't be done by small groups of people anymore. And one of the things that we're all about at Sierra is the fact that it takes an enormous breadth of expertise and discipline to solve problems in modern astronomy. Not just physicists and astronomers, but it requires engineers and data scientists. We have journalists we work with. It takes science communicators. It takes computer scientists, right? All of these people are required to solve the problems in modern astronomy. And that'll be a thread that goes through our story tonight. Okay? Okay. So, this is amateur astronomers may recognize. This is Eridanus. The kind of, sorry, it's not Eridanus, it's NGC 1300 in Eridanus, right? One of the kind of interesting aspects of astronomy that's different than other branches of science is that no human has ever been farther from Earth than the moon. But all the stories that you hear about from us astronomers, all the stories I'm going to tell you about tonight, are from things that are, for all intensive purposes, infinitely farther away. And we can tell you all kinds of things about the distant universe, about the size and the age and the life and the makeup and the composition and the chemical composition of these faraway places, because as astronomers we have had to harness technology and all the varied branches of human knowledge that we have in order to understand these places that no human will ever be able to visit. And then we have to figure out ways to convince ourselves that we're thinking in the right ways. That's what the whole game in astronomy is. And so the story we're going to tell tonight is very focused on just 50 years or so, 60 years or so, to tell you, or to attempt to tell you, how astronomy changes in a human lifetime. So the common thread is going to be that technology always is what we lean on today. Technology is really what has enabled humans to discover all the things about the universe that we know. And that's always been true, and is going to be true going into the future. And seeing more, harnessing technology to capture information that our senses and bodies are not able to without the technology is what actually helps us understand the universe and ultimately the thing we all care about, which is why are we here and what's our role to play. Okay? So, let's do that. So, the universe is old, it's awesome, it's mysterious. I don't think astronomy is ever going to be done because we think we answer questions, and as those of you who have been exposed to astronomy before know, or listened to Carl Sagan or Neil deGrasse Tyson know, is answering one question leads to 1,000 more, always, right? So it's very gratifying science to be involved in, but it's never going to be done because the universe is a big place. The career of an astronomer may only span about 50 years. Okay, so I got my bachelor's degree in 1991, and I graduated from high school in 1987, so that's where we'll start. And so we'll go from then to till today, and then we'll project a little bit ways into the future. I don't know how old I'll be when I retire, but let's assume it'll be a long time from now. So, okay? And so really this is what we're trying to do. I'm trying to illustrate how our understanding of the universe has changed just in my career as an astronomer, not even over the entire history of astronomy. Okay, so let's start 3 decades ago in 1987. What did we know about the universe? What was our picture of the cosmos around us in 1987? Okay, so I can't tell you everything, but let me tell you a few things. We knew then that the Earth was our home. We had just 10 years previously, for the first time ever, taken a picture of Earth and its partner, the Moon, when Voyager was outbound towards Jupiter. So that at that moment, was the first time, just barely a decade old, that we really had seen and understood that the Earth was a world unto itself in space. The Earth and the other planets were the only planets we knew about. Okay, so 1987 was 10 years after Star Wars. Anyone remember the premiere of Star Wars? Anyone watch Star Trek? So it's about 20 years after Star Trek, right? So George Lucas and Gene Roddenberry had convinced us there were planets around other stars. But the only planets we knew about were this one and the ones around the sun. Okay? Pluto was still a planet then. We'll talk a little bit more about that. I could go on for that for a long time. Okay? The largest telescope in the world was the 5-meter at Palomar. It had been the largest telescope in the world since it was built in 48, is that right? Yeah. And it was not surpassed until 1993. Okay? So this was the largest telescope in the world. How many people have visited Palomar? Right? Yeah. It's a great telescope. Fabulous. Big old Art Deco observatory. It's fantastic. Okay? I actually have observing time on Hale in my observing log. So that's a story for another day. Okay, so this was the largest telescope in the world. The Hubble Space Telescope, as Jim had said, had not even been launched. They were working on it. They had built it. They were getting ready, but it hadn't been launched yet. And so all the things that you and I associate, all those beautiful pictures, all those discoveries, they hadn't been made yet. It's kind of one of the remarkable things about astronomy today is that people think about astronomy through the eyes of this telescope. But it hadn't been launched at the moment that I started my career in astronomy. Okay. Amateurs were slowly discovering Dobsonians. This was maybe near the beginning, but people were starting to build them. There were still, Schmidt-Cassegrains dominating the world. The amateur telescope makers were slowly discovering new things. I'm an amateur telescope maker, as Jim said. So, but in those days, we hadn't yet figured out how to build the kind of classic truss Dobsonians that you see now. Okay, they were all solid tubes, built the way John Dobson said we should build them. And so this is what amateur astronomy looked like. Big aperture wasn't common yet, right? So kind of 10-inch telescopes, 12-inch telescopes. Those were big telescopes when I first started in this state. Today, people have 36-inch telescopes. I have 22, right? So telescopes have certainly gotten bigger. Any astrophotographers? So in the olden days, we photographed on film, okay? And you had to do some home chemistry. There was this whole game you played called Hypering, where you took film you bought at the store, and you could make it more sensitive, basically higher ISO, by exposing it to gases in a low pressure chamber at home. Okay, that makes your film more sensitive to capture dim stuff. But people were attaching cameras to the back of their telescope to do photography and doing long-term guided exposures to capture anything on film. And it's a very niche corner of the hobby, maybe, and certainly not as prevalent as it is today with digital imaging. Okay. The most distant object known in the universe was a quasar, that little dot there. So quasar is a name, means quasi-stellar object. At that time, we did not know what the quasars were. Hubble actually resolved that mystery for us. They're supermassive black holes at the centers of galaxies. But the most distant one, astronomers think of distance in this parameter we call redshift. The bigger that number, the farther away the object is. So at a redshift of 4.5, that quasar, that object, we didn't know what it was 12.4 billion light years away from Earth. Okay? So, we didn't know what it was, but we knew how far away it was. And they look like stars. You can see these some of these in your telescope in your backyard. The last supernova in the Milky Way was in 1604, which was before the invention of the astronomical telescope. Okay, so this is the supernova remnant. It's the cloud of exploded material that gets blasted out from the star when it explodes. This is called Kepler's supernova, and it was naked eye. It exploded, five years before Galileo first started looking at the sky. So in all of modern astronomy, there's never been a supernova in our own galaxy that we've been able to observe. The average for a galaxy like the Milky Way is supposed to be 1 per 50 years. And there has not been one in 400 years in the Milky Way. So astronomers are just like sitting around like this. We would love it if there were a supernova. Okay, but there hasn't been, not in the Milky Way. There have been plenty farther away. But seeing one up close would be totally different. Okay. But the frontier is always on the move. And on the 23rd of February, 1987, something happened. Does anyone know what happened? There was a supernova in a galaxy next to the Milky Way. Okay? So this is called supernova 1987A. This is the before picture, right? So astronomers always publish these before pictures with the arrow pointing at the star that exploded. This is the after picture. This was in one of the Magellanic Clouds, in the Large Magellanic Cloud, which is a small satellite galaxy that orbits the Milky Way. But you cannot see it from the northern hemisphere, at least for much of the northern hemisphere. You've got to go pretty far south to see it. Okay? But this star exploded on the 23rd of February, 1987, and it was only 168,000 light years away. So not in the Milky Way, but closer than any other supernova we'd ever seen. And astronomers wigged out.
It didn't explode, that's what you saw.
Sorry, yes, okay, yes. Okay, so we will use the astronomer convention of saying the day it exploded is the day we detected it. Yes, but astronomy is a time machine. We won't talk about that because light, the speed of light is the maximum speed of the universe, and it has a finite value. So it takes time for very interesting information to propagate from there to here. Yeah. So this exploded 168,024 years ago, and yeah, just reiterated. Okay? So, the interesting thing about this was that we saw the light. Okay, and that's always the signature. And there's been a long history of amateurs discovering supernovas. This used to be one of the things you could do to make yourself famous as an amateur. Lots of these are being discovered now by robotic telescopes. They're just kind of constantly scanning the skies. But every now and then you'll still find an amateur who's the one who discovered these. Okay? But the interesting thing about this supernova is that it was close. But because it was close, there's something else that happened. Okay? And that other thing that happened is that associated with the supernova was a nearly undetectable rain of subatomic particles expelled by the supernova that showered the Earth at the same time. These subatomic particles are called neutrinos. They are associated with various nuclear reactions and generated. The neutrinos are very fast-moving and they interact very weakly with matter. Okay? And so this supernova generated 10 to the 57 neutrinos. Now, just by happenstance, we were inventing the science of neutrino astronomy at that time. And this is a picture of the Kamiokanda neutrino detector. It's a gigantic 50,000-ton vessel of water, very pure water, down in a mine in Japan. Lining the walls are these little cameras. Okay, you can see the scientists in a rubber life raft there going around checking the cameras. And what happens is, when the scientists are in there, the neutrinos come streaming through the water, and there's so much water and so many neutrinos that every now and then the neutrino interacts with some of the water and generates a little burst of light, which we can detect. Okay? And from 1987 to 8, we detected 24 of those 10 to the 57 neutrinos. Okay? 24 out of that 10 to the 57. There have been, and I'm not joking, 10,000 papers written about those 24 neutrinos. Okay? 24 is enough for us to tell they associate with the supernova. Okay, so this is the beginning of what today we call precision astronomy. Our ability to measure and discern what is going on in the universe is so precise, and we've done so much of it, that we can tell when there's 24 extra neutrinos that there shouldn't have been. And so today, this has grown into a whole bunch of neutrino experiments, which I won't tell you about. The most famous one is at the South Pole called IceCube. And some of you may know about that. But neutrino astronomy is part of the landscape. Okay, but it started here. Okay? So, let's fast forward to today. The world's very different today. So I've been a professional astronomer now since, when did I get my degree? 99? Okay, but graduated in 91 from Oregon State. But today, the world's very different. Okay, so apparently Pluto is not a planet now. We can argue about that. Okay. Next Saturday, I'm giving a talk up at Evergreen Aviation in Winville. We're going to talk about Pluto and planets, so we'll argue about this there. Okay, but Pluto's no longer a planet. Okay. Amateur astronomy is getting bigger, right? So big dogs and big telescopes are certainly part of the landscape. This is also enabled by technology, right? The thread here is that technology changes the landscape, both for professional astronomers, but also for amateur astronomers as well. The whole thing that makes big aperture telescopes possible now is this kind of modern truss design that allows us to build telescopes that are massive and structurally sound enough to do the job with the big optics. Amateur astrophotography is utterly mind-blowing, okay? These are both amateur astrophotos. This is from a guy on the web called Astrolord. I have no idea what his real name is, but he posts under Astrolord. That is a digital picture of Jupiter taken from Earth. What enables this kind of picture to happen is digital image processing. They take a video of Jupiter, they shoot 20,000 frames of Jupiter, they take the 25 best ones, they stack them together, and it makes something that if you go get, I'm sure many of you like me have your National Geographic from 1977 when Voyager went past Jupiter, that picture is better than any picture Voyager took. It's amazing, right? Similarly, the image and the detail and the nebulosity that you can get out of deep sky objects is remarkable as well. Okay? Also enabled by digital image processing. Okay? Modern detectors, modern digital detectors, are so much more sensitive and so much more capable than buying some Kodak film from Kmart. Right? Okay, so this is there's lots and lots of amateurs now who do this because not only is the technology better, it's also more affordable. And it's easy enough to use and implement that you see a lot of this among the amateurs as well. Okay? So it certainly has been changing on the front for us as amateurs. In terms of planets, though, our understanding of planets in the universe has grown dramatically. Every time I give this talk or my exoplanet talk, I have to update this slide. We are currently discovering about 500 to 1,000 planets per year each time I have to update this slide. Okay, so currently, as of yesterday, I didn't check today, but yesterday when I updated this slide, there are 7,043 known planets in the exoplanet catalog. Okay, and that's not just planets. There are 4,958 solar systems. That means planetary systems which have one or more planets in them. So it really is like Gene Roddenberry and George Lucas told us. Stars have planets around them. And when we started discovering planets, which just has happened in the last 10, 20 years, one of the questions in astronomers' minds was, what fraction of stars have planets around them? Is it 1 in 10? Is it 1 in 4? Is it half? We have discovered planets literally around every kind of star you can imagine. We've discovered them around dead stars. We've discovered them around double stars. We've discovered them packed in close around dwarf stars. We now think, as near as we can tell, that it is far less likely that a star doesn't have a planet than that it does. So we assume now, by default, I think in general, that every star has planets around it. Okay? So there's lots and lots of planets. The number of planets now, right, those of you who are scientists or practice science, right, you know this is true. This is what drives science forward. Data. We used to know about 9 planets, and then we decided we had 8, which was wrong, but we decided that. But now we have 7,000 planets, and that completely changes the landscape of what you think about what kinds of planets are possible, how do they form, how do they interact with each other, how do their properties depend on their parent stars, right? All of that information, all of those kinds of questions can be answered now because we have so much data to work with. Okay? Hubble has had a storied career. It launched in 1991. There was a little bit of tragedy there at the beginning. Okay? But we've worked on it. There's actually been tremendous amounts of science that has come out of the repair of Hubble, both in terms of image processing and our understanding of optics. All of that has led to remarkable things. So the tragedy, in retrospect, 3 decades later, it was painful, but there's good things that came about it. Okay? But Hubble now, it is plausibly on its last legs. The plan has always been, after the last repair mission, for it to be deorbited when it dies. There have constantly been rumblings that maybe we shouldn't do that. And so I don't know, I'm not in those circles, but I have started in the last couple of years starting to hear conversations about can we robotically service it. And what that really should tell you is it's a testament to how much we as professional astronomers depend on this instrument. Yeah, we have bigger telescopes, I'll tell you about those in a moment, right? But Hubble itself has been the foundation for this tremendous astronomical legacy. And despite the fact that it's 35 years old now, we still, every single day, rely on it and are making discoveries about it, making discoveries with it, and it's still, every single day, transforming the things we know and understand about the universe. Okay? But let me just tell you the thing that I have always regarded as the most important thing that Hubble did. Okay? So Hubble's field of view is about the size of Roosevelt's eye. If you take a dime and you hold it out at arm's length. Okay? So you take that dime and you hold it out there. However big Roosevelt's eye looks to you, that's about the size of any Hubble picture that you see. Okay? And so one of the things that we asked Hubble to do, which had never been done with any telescope before Hubble, was we asked it to take a type of photograph that is now very common in astronomy called a deep field. That means pick a spot in the sky. Ostensibly, we picked a place where there was nothing we had ever seen there before. And then you look at that spot over and over and over again. You basically do a long duration exposure. Okay? So, Hubble has done many, many of these, but this particular one is the Hubble Ultra Deep Field. Okay. We looked at this spot. It's right off Eridanus for 53 days and just exposed. And every single fleck of light that you see in that picture, with the exception of the 3 things that have little starbursts around them, Okay, those are stars in the Milky Way. But every single other thing in that image is a distant galaxy. So something we didn't know before Hubble did this was how many galaxies are there in the universe. But now we know, because no point on the sky is really any different than any other point. And so if I take this little spot the size of Roosevelt's eye, and I count the number of galaxies I see, and I multiply up by how many Roosevelt eyes would take to cover the whole sky, you get something like 600 billion galaxies fill the cosmos. Okay? And we're going to come back to that in a minute. So just think about that, because galaxies are, despite the fact that we know about galaxies now, which is less than 100 years, but we know about galaxies, there's still some big mysteries here that we don't know about, okay? And it starts with images like this. I'll tell you about that in a minute. The thing that I work on, which Jim mentioned briefly, is that we have now learned to look at the universe not just with light, with telescopes, not just with subatomic particles that come through you and you don't even know it, but also with gravity itself. Okay, so here in the Pacific Northwest, we are part of this story. In the United States, we've built 2 of these detectors. They function basically as a single observatory together. They're called LIGO, the Laser Interferometer Gravitational Wave Observatory. One is in Livingston, Louisiana, and this one is just west of Tri-Cities on the edge of the Hanford Reservation. Okay, how many people have been to either of these? Anyone? Okay, so in Hanford, they have just built, right during COVID, a brand new visitor center. And so if you're in Tri-Cities, you like the Taco Bell there or something, and you go to Tri-Cities, right, you should drive out, you can drop into the visitor center, they'll tell you all about LIGO. You can arrange group tours, so I was talking to Jim, so people can go out and visit, they do school groups, the whole 9 yards, okay? But what is this thing, right? So I love the name. It says exactly what it is. It's a laser interferometer. That's the kind of instrument it is. And it's a gravitational wave observatory. It's observing the universe not with light, but with gravity. Okay? And so that interferometer, there's a corner building here. There's a big giant laser in there. Okay? And then these arms make up the thing we call the interferometer. And from the building out to the far end, it's a 1 meter diameter steel tube that's been vacuum evacuated. All the air's been taken out of it. And we shine the laser down that arm, 4 kilometers. Okay, it's about 2.5 miles. Okay? And there's a mirror down there at the other end. And so I shoot the laser, and it goes and hits that mirror, and it comes back, and I time how long it took to do that. And I do the same thing down the other one. And the reason we do that is because what gravity does, what these gravitational waves do, and I'm not going to tell you about those, but there's a whole talk about gravitational waves, but what gravitational waves do is they change the amount of time it takes the lasers to fly up and down those 2 arms. It stretches the arms and it compresses the arms. Okay? So Einstein thought of this in 1917. He famously did a calculation that said this will be impossible to do. But you and I live in the future. And we have lasers and supercomputers and advanced optics technology. And we built this instrument. And in 2015, on September 14th, for the very first time, we observed the gravity from 2 black holes spiraling around one another and then ultimately merging to form one new, single, bigger black hole. It was the culmination of a century of imagining that this could be done. In 1972 or so, Ray Weiss, who's a colleague of ours at MIT, famously sketched out the idea for LIGO on a napkin, and it took till 2015 for us to be able to do it. Now, every discovery is awesome. Gravitational waves exist. We can do astronomy on things that don't even emit light, because they do have gravity. But there's always mysteries. And the big mystery about this is if you had asked me or any other astronomer on September 13th, what the biggest black holes that would form from stars were, we would have told you 10, 15 solar masses. Both of those are roughly 30. We have no idea how to make 30 solar mass black holes. But when they merge, they make an even bigger black hole. They make something close to 60. And if I were to take that merged black hole and put it down on the center of Oregon, it would stretch from Eugene all the way up to John Day. But on September 13, in 2015, we had no idea black holes that size existed. And now we do. We have no idea where they come from. But we know they're there. Okay. So this has become a total enterprise. But let me show you. I'm going to do this both at the beginning and at the end when I tell you about this. So let me start with our data. This is what modern astronomical gravitational wave data looks like, right? It looks like squiggles. It looks like graphs. Okay. And the problem with this is that all of us, virtually everyone in the world today, has grown up learning about astronomy through the eyes of Hubble. So when we make the most important discovery in the history of astronomy in the last 200 years, and I send my data to the editor of the Oregonian, they're like, go away, kid, you bother us. Because we're used to understanding astronomy through the eyes of Hubble, right? People don't want to see graphs. Okay? But this is what our data really is. And the reason there's no better way to represent this is our bodies are not built to experience this data with any of our senses. None of you has a gravitational wave detector in your elbow. I don't think. Does anyone? Okay. Okay. So one of the things we spend a lot of time as gravitational wave astronomers is figuring out how to make this data, let's call it real for people. Okay, and so one of the things, those of you who are physicists know this, right? One of the first things we teach you in physics is that the world is just waves. A wave is a wave is a wave. Water wave, sound wave, light wave, radio wave, they're all just waves. Waves on a guitar string, right? They're all just waves. Which means gravitational waves are just waves too. Which means they have all the properties of waves. Which means any way that I represent waves for all of you normally, I can represent the gravitational waves that way. So, if I steal your phone, on your phone is a whole bunch of squiggles that look just like this, that your phone thinks is Taylor Swift. If I replace your Taylor Swift music with these wiggles, and your phone pushes it out through the headphone jack, it turns them into sound. Just like it turns those other wiggles into Taylor Swift. Okay? So, I'm going to do that. I'm going to push these wiggles out through my headphone jack, which should come out through the speakers. We tested it, so it should work. Okay? And you will hear this data. Okay? It's in real time. It's only about half a second long. So that's how long we saw the total in spiral. Okay, that movie I was showing you was slowed down so you could watch it. But it was only a half a second long. Okay? Now, it's going to play twice. The first time, it's very low pitched. The second time, we just push it a couple octaves up so that your ear can hear it a little bit better. But it's the same data, just pushed up by an octave. Okay? So let me play that, and then... hear that little drop? Or the thump? Thump. Chirp. Okay? So that's what we call a chirp. It has to do with what this gravitational wave does. As the black holes get closer together, the gravity gets stronger, which is why the signal gets louder. And as they get closer together, they start going faster, which is why the pitch goes up. That's what makes that little chirping sound. Okay? So that, as gravitational wave astronomers was completely used to this. And so Kip Thorne at Caltech, who won the Nobel Prize for this, he was one of my postdoc advisors. When we discovered this, right, we just walked in and they showed the graph to Kip, and he knew. He's like, my God, we found it. Right? I mean, he didn't even wait for the analysis. He knew. Because we know There's very few ways to make this in nature except doing what nature has done. Okay? So, there's lots of other types of signals that we can do, but we've been doing this now for many years. This is a representation of our gravitational wave catalog. So this, you can get this online at our site at Northwestern. This is a plot we make. You see this around a lot. This is all of the black holes that we have discovered with LIGO. Okay, so all the blue ones are two things that have merged to form a third thing. Okay? The orange ones are neutron stars, another kind of stellar skeleton that we've discovered with LIGO. All the yellow ones are the neutron stars we knew before LIGO, and all the pink ones are the black holes that we knew before LIGO. Okay? Within 6 months or so, I don't actually know the schedule, I should, I'm sorry, we are going to release the next version of this catalog, which is going to double the number of black holes. Okay? So the catalog is growing every day. We're discovering these at a rate of 1 or 2 a week. There's an app you can get on your phone. It'll tell you every time you think we have made a discovery. Okay? So, that is the world today. And I could leap ahead to the future, but since I first wrote this talk many years ago, the future has arrived. So let me tell you about the beginning of the future right now. Now, I'll just tell you about a couple of things. So there is a mission that has been out for several years now called Gaia. Okay, so this is led by the European Space Agency. Like many modern astronomy missions, the data becomes public instantly, which means us as professional astronomers, we download it, we start working on it, we write papers, but it also means people like you who are bored with your life as a dentist can learn a little Python and download the data and do your own processing. Okay? Well, what does Gaia do? Gaia is mapping the position and movement of 1.8 billion stars in the Milky Way. So this is showing its location here, approximately the Earth, and radiating outward the sight lines for all of Gaia's measurements. It will be the most precise stellar catalog ever made of stellar positions and stellar motions, which will allow us to not only map out the structure of the Milky Way, but also to understand what the local motion and dynamics of stars in the galaxy actually are. They have been through 3 data releases. The 4th one's coming soon, in 2025, I think. This is one representation of the data. This looks like a photograph. It is not. It is a computer-generated image where a dot has been placed for every star that Gaia has measured. And it looks just like the galaxy. This is precision astronomy. And it's more than precision astronomy. It's big data astronomy, which is one of the current challenges. The technology is allowing us to discover more, but the amount of data that we have to work with is getting out of hand. We have to develop tools and techniques, not only to store the data and move the data around and make it available, but also how to process it and understand it and figure out what information is contained in data like this. Okay? But there's lots of cool data. So for instance, we are measuring the proper motion, as we call it, the velocity vector of all of the stars in the Gaia data set. And this is the motion of all the stars that are naked eye in the Gaia data set for the next 400,000 years. So I can make the star charts that the Sky Telescope will publish 400,000 years from now from the Gaia data. Which is awesome. Okay. If you trust that the laws of physics are time reversible, I can run this backwards to tell you what the constellations looked like 100,000 years ago. Right? So what do you want to know about that stuff, right? One of the biggest mysteries in the world right now is where are the sibling stars that were born at the same time as the sun? Well, the way you figure that out is you find stars that have the same chemical composition of the sun and are moving through the galaxy with similar velocity to the sun. This is the kind of data you need to do that. Okay? Of course, this has been a long time coming, right? Last time I gave this talk, right before the pandemic, right? This hadn't even launched yet. Okay? But the future is now. It's here. Okay? And it's just beginning to kind of understand what we're going to learn from JWST. But let me tell you some of the things that I am already impressed with. We have already broken the distant record. Okay? So the new redshift record is 14.32. Okay? That's just 290 million years after the Big Bang. It's this galaxy right here called Jade's GS Z14O. Okay? The problem, the mystery, is we have no freaking idea how to make galaxies 290 million years after the Big Bang. We can see it's there. We can tell it has hydrogen in it. We can tell it has oxygen in it, which generally means it's already had stars go through a stellar lifetime. Okay? How does that happen 290 million years after the Big Bang? This is why I have a job. Okay? Okay, so this is the new distant record. And if you're paying attention, this keeps getting broken like every 2 or 3 months, right? Because they just keep making new observations. They're like, oh, new farther one, right? So it's been kind of falling at a regular pace since JWST was launched. This is a picture of one of the Abell clusters that Hubble took. Okay, so these clusters are famous because if you look closely, there are these little distorted arcs that are actually funhouse images of galaxies. And what happens is there's some galaxy far away in the universe. The light from that galaxy passes through this cluster of galaxies that's in the front. And the gravity, mostly from the dark matter, bends the trajectories that the light travels on. Okay? And so we can measure all of these little galaxy arcs and use it as a way of probing dark matter in galaxy clusters. Okay, so I've co-aligned this with a picture of the same field from JWST. So what I will flip back and forth, but pick your favorite little dot there, and I'll switch back and forth with the JWST image so you can see how the precision, the ability of the instrument is changing what we're able to do. Everyone ready? Got your favorite one? Okay, here we go. Okay, so you'll notice that the detail itself increases dramatically. But if you pay attention, you'll also see new galaxies that you couldn't see before, right? So I'll just flip back and forth a couple times so you can watch the two of them, right? So pick something new each time we flip. Okay. So this is the kind of thing that we're doing a lot of now. I think those of us who are amateurs are used to this. Every time you get a brand new telescope, you go look at things you've already looked at before, right? But that's because you thought you knew everything about it and you want to make sure that you know everything. So this is sort of what it does. This is my absolute favorite thing about JWST. What is this? It's not Saturn. It is Uranus. Or no, it's Neptune. Sorry, it's Neptune. Yeah. And if we had not flown Voyager to Neptune, when we flew JWST, we would have discovered the rings of Neptune with JWST. Because we can see them from Earth, which we couldn't at the time we launched Voyager. Right? And again, if you go out your National Geographic, this is one of the big discoveries when Voyager went past Neptune. Okay? So this is what technology does, right? It confirms older discoveries, but it also gives you a sense of what the discovery potential is by the power of the instrument. So. And then this, those of you who, we were talking about lensing just a minute ago, this is called an Einstein ring. Okay, so when two objects are exactly perfectly aligned, then the light is bent equally around the lens, dark matter or the star or the black hole that's creating the lens, and makes these perfect rings. And Einstein, it's called an Einstein ring because Einstein had predicted this, but in the typical fashion of astronomers were like, the chances of that happening and making a perfect Einstein ring are impossible. And now JWST can find it. So, okay, so the universe, right, nothing's impossible, the universe is a big place. Okay, so let's jump to the future. If we go 3 decades in the future, and you and I come back, some of us will be older, some of us will look older, okay? And we talk about what's going to be different 3 decades from now. One of the things that will be true is not only will that exoplanet catalog be huge, but we will have reached the point where we can actually understand what the properties of those individual planets are. We right now are doing this. We can do it for some planets, not all. But our goal here is to detect planets that are similar in size, similar in composition, similar in temperature to the Earth, because we're obsessed with life on Earth. Okay? But what that means is not only being able to measure the size and orbits of the planets, it means being able to measure their atmospheres. Okay? And these big telescopes, some of you may remember the first press release from JWST, it's all about measuring the properties of the atmosphere. Okay? And we are rapidly approaching where that's going to be commonplace and where it's going to be possible for planets that are the size of the Earth. So 30 years from now, this will be a solved problem. I predict. I'll bet you Dr. Pepper and a jelly donut. Okay. One of the things that we haven't talked a lot about is the importance in computing and simulation. So I do a lot of computing and simulations. My group simulates the Milky Way galaxy. And more, in order to understand the data that we're collecting, we have to be able to push the laws of physics into the boundaries where you can't do it with pen and paper anymore. It's, as we say in the biz, nonlinear, and it is very unstable to small perturbations, and we just can't understand it unless we can do these massive computer simulations. Okay, and we do that on many fronts. I work in gravitational waves, so we do a lot of colliding black holes. This is what we need to understand that gravitational wave data. My group simulates entire galaxies. So we basically simulate the lives of all the stars in the Milky Way galaxy and tell you what it looks like today, and in particular what the stellar graveyard looks like. And then those supernovas are still pesky. We haven't seen one up close. And so we don't actually know how stars explode. And so we're trying to simulate them on computers to try and understand exactly what all the properties of exploding stars are. Okay, so increasingly computer simulations are used side by side with data, with observations, and with computers at the same time. This is about to start. This has been the dream for a couple of decades now. This is called the Vera Rubin Observatory. It used to be called LSST, the Large Synoptic Survey Telescope. We still use the LSST name associated with Vera Rubin because one of its programs is to survey far and deep in the universe, so that's called the Legacy Survey of Space and Time. But Vera Rubin is, it's almost there. It's almost there. It's been built on a mountaintop in Chile. Its goal is to take a 5-color movie of every point on the sky that the telescope can see every 3 days. Okay, for a decade or longer. Okay, so what does that mean? So here's the telescope. Okay, you can see the engineers right up there working on it, give you a sense of the size. It's very fast. I think it's F1 or something. Some of the amateur astronomers may know. It's a very fast telescope. Okay, but it'll start in just about a year. It's going to collect 20 terabytes of imaging data per night. Okay, so for those of you who don't think in terabytes, that's about 15 million iPhone photos. Which is, what, a tenth of what you have on your phone right now? Okay. 20 terabytes a night, which we then have to distribute to the astronomical community. Okay. All told, the final data at the end of its first planned science is 15 petabytes, which is 11.3 billion iPhone photos. That's a lot of data. Okay, so there's all kinds of problems, right? Storage is one problem. Okay? And not just storage backup, getting it around the world, but the real problem is how do you sift through all that data? Right? So a big part of our community right now is invested in machine learning and AI and data processing. All the stuff that you hear about that's going on right now has been being worked on in the astronomy community for 10 or 15 years because we knew this problem was coming. Because you can't have a graduate student sift through 15 million iPhone codes every night looking for supernovas, or looking for asteroids, or looking for cosmic string collisions, or looking for whatever, okay? But you have to teach a computer to sit through and find stuff and decide, am I going to tell the humans about this? And then which pile to put it in. And that's a really, 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 really hard problem, which we're working on. But data's coming next year, so. Okay, so this is the future. And 10 years from now, when we give this talk, our world in astronomy is going to be completely transformed by this data. Okay, we think we speculate about what it'll be like, but we really don't know. Okay? The number of discoveries that come out of this will transform astronomy. Because there's going to be stuff we have no idea what it is. Okay, I mean, there's been a whole bunch of Starlink satellites and all that, but yeah, stuff we don't know what it is. Okay, so this is at the forefront of data science. We are rapidly approaching the next generation of telescopes. We are going to build 30-meter telescopes on the ground. Current biggest telescopes are in the 10-meter scale, 10 or 11 meters. We're going to increase that by a factor of 3. This is the Giant Magellan Telescope. They are already working on this. They have cast, I think, all of the mirrors at this point. Anyone been to the Mirror Lab in Arizona? Okay, yeah, some of you. Okay, so this is where they make these. But you can see it's multiple mirrors together, and all told it's like 28 meters, 29 meters, something like that. Okay. One of the things that's happened over the history of astronomy is each time we make a giant leap in aperture, then that aperture dominates in astronomy for decades. The Hubble telescope was the largest telescope class in the world from 48 to 93. Keck, 10-meter scale, has been the largest telescope from 93 till whenever these get in the 30s. So for the next 50 years, the biggest discoveries on the planet will be made by telescopes this size. Okay? Similar to LSST, we have big data problems with this because we can see a lot of stuff. Okay, so this is what the future is going to be like on the ground. So let me take the last few minutes here and tell you about LISA, which is what I work on. So we are already talking about the ground-based gravitational wave detectors that are going to replace LIGO. The United States is going to build one called Cosmic Explorer. The Europeans are going to build one called Einstein Telescope. They're currently looking for sites for those observatories. It will take them 15 or 20 years to build them. But 10 years from now, we're going to build a gravitational wave observatory in space called LISA, the Laser Interferometer Space Antenna. Okay? And I forgot to, is there anyone named Lisa in the audience? I normally bring stickers. Okay, good. Okay, I didn't fail. Okay, but if you know someone named Lisa, email me, I'll send you a sticker. Okay. Okay, so LISA is kind of just like LIGO. Remember, LIGO was a corner with 2 arms and then mirrors at the end. Okay, LISA's the same thing, except instead of a big tube, we're just going to shoot the lasers through outer space between 3 spacecraft. LIGO was 4 kilometers from one corner to the center. LISA is 2.5 million kilometers from spacecraft to spacecraft. Right. Okay. This was just approved by NASA and the European Space Agency in January, which means they're spending money on it. The prime contractor is being picked. It will be announced this coming January, and roughly 10 years from now, this should launch. Okay? We're going to see more gravitational wave objects with LISA than any other gravitational wave observatory in the world. LIGO's been observing since 2015. We have a catalog of about 200 objects. By the 6-month mark with LISA, we will have observed 10 to 50,000 gravitational wave sources in the Milky Way galaxy. That's what my group looks like. We will have observed between 10 and 1,000 supermassive black holes in colliding galaxies to the edge of the visible universe. Right? LISA is going to transform the face of gravitational wave astronomy. It will cost, all told, a couple of $1 billion. NASA and the European Space Agency doesn't let you spend a couple $1 billion unless they're confident that you know what you're going to do. And they don't like us to come and say, yeah, we can totally do this, guys, trust us. And they don't like that, okay? So what they do is they make you fly a technology demonstration, okay? So in 2015, at that moment we were making that big gravitational wave discovery, we flew a mission called LISA Pathfinder. It was basically a single LISA spacecraft where we had taken that 2.5 million kilometer arm and shrunk it down to 30 centimeters. And what we had to prove was that we could precisely measure the location of our mirror in outer space. And so that cube up there is the mirror that we use. It's a cube of gold and platinum. It's about 5 centimeters to a side, weighs about 2 kilograms, and it floats all by itself in the middle of that LISA spacecraft. And nothing can touch it because we're trying to measure gravity, right? So we're waiting for gravity to push it around. But if anything touches it, that means gravity didn't push it around. So the spacecraft's entire job is to protect it from everything except gravity. And if the cube goes in some direction, because gravity pushed that way, the laser bounces off that shiny surface, and we can detect it. Now, in my hand there is a replica of that cube. Because the real cube is made out of gold and platinum. And they don't let people like me who touch gold and platinum things. We lick it, we get fingerprints on it, it's bad. Okay? This one is made out of tungsten. Because tungsten has almost the identical density, 98%, of the real gold and platinum cube. So there in my hand is a one-to-one replica of the LISA test mass, the mirror that we'll use to measure gravitational waves. So I was at Goddard, that's where I took that picture, and they were handing this around, they made like 3 of them. And I was like, I am going to give a public lecture, and I take that with me. And they're like, sure, just bring it back the next time you come to Goddard. And so I took it off, and I went and I gave public lectures with it. And I went back, and they're like, you have the cube? I'm like, yeah, here's your cube. And they're like, what have you been doing with it? I'm like, I've handed that cube to 3,000 people. And they're like, oh, you keep the cube. So, I have the cube. Do you all want to see the cube? Yeah, you do. Okay, so here's the deal with the cube. Those of you who know, tungsten is very dense. Okay, so my rule is you just have to be careful. Okay, if you're balancing on your head, taking a selfie or something, don't hurt yourself. Okay, but people take pictures of themselves with the cube, and I have a collection on my hard drive of pictures of people with the cube. So if you take a picture of yourself with the cube, please send it to me for my collection. Okay? Okay. So this is one-to-one scale model. This is the future of gravitational wave astronomy right here in your hand. One-to-one scale, same weight, same size. The only difference is it's tungsten, not gold and platinum. Okay? So I'll pass it around. Just be careful with it, and I'll get it back from Donald. Okay? Okay. So this is the future. Okay, so let me play some gravitational wave sounds for you, and we'll close off. So one of the things we're going to see with LISA is much bigger black holes than light galaxies. This has to do with the fact that when they're bigger, they can't get in close orbits like they can with LIGO, but when they're in wide orbits, then LISA can detect it. Okay, and so what I want to do with this sound demonstration here is I want you to experience the fact that there's real astrophysical information in this data. So I'm going to play 2 different sounds for you. They are the identical system in that they are a 10 solar mass black hole falling into a 10,000 solar mass black hole. So these are black holes formed by stars falling into black holes that live in the centers of dwarf galaxies. Okay? The difference between the 2 sounds is the first sound is circular orbits slowly shrinking. And the second sound is what we call elliptical orbits, oval-shaped orbits. And the important thing for you to listen to is that you can hear the difference. Okay? Which means there's real astrophysical data in the data. Okay? And I could do this with anything. I could change the masses, and you could hear the difference. I could change the way the orbit is oriented. You could hear the difference, right? This is not difficult to get astrophysical information out of the way it works, which is the point of the exercise. Okay? So here's the first one. It's real time. The last 1,000 moments or so. Okay, that's that chirp. As they get close together, they go faster, so the pitch goes up. As they get closer together, the gravitational interaction gets stronger, so the sound gets a little bit louder. Okay? Okay. Next one, same two black holes. All I've done is I've made the orbit elliptical, that is, it's oval shaped instead of circular. Okay? Sounds like the car you had in college, right? Okay? So what's happening? When it's oval shaped and the two black holes are far apart, there's no sound. But when they get close together, the gravitational interaction is very strong. And you hear that little pop. And then they're far apart, and then they're close together, and you hear the pop. Over time, that oval-shaped orbit becomes more circular, and the pops get closer together until it sounds almost exactly the same as the other one. Okay? So we will be able to tell you, the moment we detect these things, what the orbits are like. Okay? Okay. Last sound is what the full LISA data sounds like. With LIGO, we sit around and every couple times a week we hear something. With LISA, everything's on all the time. Okay? It's like when we were all in here talking and joking around before we started, right? You could hear everything going on, and you could separate out things that were close to you. You could separate out loud things, and if you listen hard, you can hear the conversation in the back of the room, right? That's the problem we have to solve. It requires lots of computer processing to do it. But this is what the full LISA data sounds like. It's a little bit quieter so it doesn't overwhelm you, so you have to listen carefully. If you listen, you'll hear individual sources in there. It's one of those black holes. This is what the universe is doing all the time. And 100 years ago, Einstein thought we wouldn't be able to do this. But you and I live in the future, right? Okay. So, this is the frontiers. You and I are living at this age of discovery, where humans are not just discovering what the universe around them is all about, but really pushing the boundaries of what we have any reasonable right to actually know or understand. We're probing the universe in ways that our bodies weren't ever meant to be able to do, but our imagination and our technology enables us to do. And it's a remarkable time to be learning about the universe. Of course, it depends completely on people. You can't do this without thousands and thousands of people worldwide who are working on the physics, on the astronomy, on the engineering, on the optics, on the computer programming to make this happen. And the stories I've told you are from me and 1,000 other colleagues around the world who are working on this every day. Okay? So this is what it's all about, and it's what makes it fun, and it's what makes us get up and be able to do things every day. So I always leave you with a few things to read. So here's a few books. Some of you may recognize these. There's kind of no big comprehensive book about all the things in the universe, but these are all related to a few of the different things I've told you tonight. So a little bit, for those of you who still read books as opposed to Kindles or something. I suppose most of these you can probably get on Kindle, but you can go look and read about some of this stuff yourself. So So I will stop there and certainly say thank you so much for your time, and I'm happy to take questions for as long as we want to hang out. So.
After you get your cubes to orbital speed, how do you get them to sit still in space?
So that's a great question. How do I get the cubes to sit still in space once we get the spacecraft to position? So you will notice on the cube and in the pictures, there's little indentations in the center. Okay, you can't just put something like that on a rocket and throw into space without it rattling around and destroying everything. So we actually clamp it down. Okay, we call that, it's caged, as we say. And then there are these fingers that insert into those little holes, and it pushes it out into the center of the little cavity where it floats, and then it retracts at the same time and leaves it in principal motionless right there in the center. So we tested that on Pathfinder to prove that we can do it. We're redesigning it for LISA because it worked, but we would have liked it to work better, and so they're working already on redesigning it. So, okay, there were hands around, so let's start. Yeah, here. I'll go back and forth this way.
So speaking of black hole mergers and simulations run using computer models, I understand there's this intriguing problem called the last parsec, where the models predict that the black holes stop their merge and stall out. So I was just glancing through a picture the other day that made popular press where they speculated that dark matter was a bridge. I'm just curious, this is your field.
Yeah.
What's your favorite idea on how to get over this?
So one of the things, so the reason these big black holes get together is galaxies collide and they form new galaxies. And those of you who know things about galaxies, you know, galaxies that look like spirals, they merge and then they make elliptical galaxies. But the black holes have to work their way to the center. And the way they work their way to the center is through something we call dynamical friction. They basically interact with all the stars in the galaxy. And so what happens is if the black hole's moving along and it encounters a group of stars or a single star, it imparts energy on that star, which is what puffs up the elliptical galaxy, and the black hole kind of sinks towards the center because it stops moving as much as it was before. Okay, and there's this long-standing problem, which Mel alludes to, which is, we call it the last parsec problem, because when the two black holes get within 3 or 4 light years of each other, there aren't enough stars left to make that keep happening. Okay, and so this has been a mystery for a long, long time. And so I think most of us think it's been solved, but of course we haven't measured it yet. And so there are still kind of new ideas coming out, which is this dark matter result that you've mentioned. And I've seen that paper, but I haven't read all the details of it. But the way that we think it's been solved is that when we think about that friction, as we call it, we have always thought of the galaxies as being very uniform. And so there's a whole group of us who simulate galaxies. So I simulate the stars in the galaxy, but like colleagues of mine, Kelly Holley-Bachman, who's at Vanderbilt, she's very famous for this. They simulate the fact that galaxies are not perfectly shaped, or as we say, triaxial. And so what the resolution for the last 5 or 10 years to the last parsec problem, which is the one I believe, is that asymmetry in the shape of the galaxy provides enough stars in that central parsec to drive the black holes to the final stages that they need to be at. That doesn't mean there's not dark matter. We still have no idea really what the dark matter is, and nor what its distribution is down near the center. And so it's entirely plausible that it's a combination of effects. And so that's why these ideas like dark matter, I think, are still intriguing. Yeah. So, okay. There's going to be too many questions, so I'll try to grab them when I see them.
This is in regards to the amount of data that you said you need to transpose, and you're a little on what. I saw a series recently about quantum computing and the exponential. It's supposedly going to be exponentially able to calculate and change the world forever because of the amount of. So, how is that affecting your problem of data?
So we have just recently, a group of colleagues and I started talking about this. And the reason we started talking about it is because I have too many hobbies. And so one of the hobbies that I like to fiddle around with is cryptography. And quantum computing has really traditionally been thought of mostly in the context of big problems like cryptography, because the speed of computation allows you to address the number of combinations you have to use. But the question that we've been dancing around is, can you think of the data analysis problem where you have all these signals overlapping the same way you do about cryptography? There's something you want to know that's hidden in a whole bunch of other stuff that's trying to basically disguise the fact that it's there. And so it's an intriguing idea. Certainly any increase in computational speed is helpful. But we've been trying to understand whether or not we can apply the ideas of quantum computing to our data analysis problem. And there may be, I may have other colleagues who are far beyond this than we are, but we've just started talking about this literally in the last 2 or 3 months. And so I don't know the answer to that, but in 10 years when we do this talk again, you ask me.
You will come back in 10 years.
Yeah. Jim will invite me, right? Yeah. Okay, back here, yes ma'am.
What's the one question you'd like to see answered in your lifetime?
What is the one question I would like to see answered in my lifetime? Oh, well, okay, so we can talk about SETI. I'm not going to talk about SETI, but yes, SETI would be awesome. So I'm going to tell you what I would like to be answered, but I have a standard bet with everyone that I don't think this will be answered in my lifetime. But I would really like to know what the dark matter is, right? So dark matter is a problem that has been around for a century, right? I have a whole dark matter talk we can do sometime if we want to the next time I'm here. But it was discovered originally in the 1930s by an astronomer named Fritz Zwicky. And he was measuring the motions of galaxies and counting how much light he could see, and he's like, there's stuff here we can't see. And then Vera Rubin, who the Vera Rubin Observatory was named after, her and her colleagues in the late 60s and early 70s really kind of nailed down the fact that dark matter is actually there. And so we've now, for decades, been looking for what it is. I work on some experiments for this. We have discounted some ideas. We have thought of new things it might be. And just really nothing has really stuck. And every time we have talks about this, right, we have new ideas, we get excited, we go do searches, and we're reaching the point in the kind of current dark matter searches where every time I go hear talks about this, I raise my hand and say, when are we going to give up on this idea? Because it doesn't look like it's going anywhere, right? And so I think we're just kind of in that state where we know it's there. But our data is getting better, and it's convincing us more that it's there, but we just don't have any good ideas for what it might be. And I would love to know. I have some kind of probably bonkers ideas. So I'm a big fan of the idea that maybe it's a whole bunch of different things that together masquerade as this one thing we're calling dark matter. I like that idea, but I don't know how to make it work. So, we think about this and we talk about it. I would love to answer the dark matter problem. Yeah. Okay. Let me go over here and then I'll come back. Yes, sir.
Were you pointing at me?
Yeah.
So you set me up by raising the dark matter question while I was trying to get your attention. So my question is, which of the technologies you told us about do you think has the best shot at answering that question about the nature of dark matter?
So I have a little bit of a prejudice towards LISA and gravitational waves. Okay? But the reason is because for a long time, so there's basically two competing ideas for dark matter. There's something called MACHOs, okay? Massive astrophysical compact halo objects. The dark matter is in compact, dense objects that orbit galaxies. Okay? The other are called WIMPs, weakly interacting massive particles, things like neutrinos, which are a gas that surrounds the galaxy. Okay? The discounting, the reason MACHOs are out of favor is because an experiment was done right at the time I was in graduate school to look for MACHOs, and they found some, but not enough to account for all the dark matter. And so they're like, well, this can't be the dark matter, which is why, as I was telling this woman over here, I like this hybrid idea. Maybe it's many different things. But if the MACHOs are there, they will emit gravitational waves, and LISA will be able to see them, right? So I think that's why I'm in that mode. The discovery of these big black holes by LIGO has also driven people back to wondering whether or not MACHOs are possible, because there are black holes we didn't know the size of that exist now, that we're confident exist, and we had never accounted for that in our dark matter thinking before. So I'm kind of in the boat where I think we're going to go back to gravitational waves, and gravitational waves are going to tell us something about dark matter.
What about modified gravity instead of different kinds of?
Well, that's a big can of worms, and we can talk about modified gravity if you want to, but that's still possible.
Can we take one more question?
Yeah, let's take one more.
And then,
There have been many hands. Who's had their hand up the
for a while
longest?
after.
Okay, we'll go here in a second.
So the universe is expanding,
Uh-huh.
and you guys are trying to reach out further all the time and visualize and measure. You're engaged in a race
Yeah?
against time.
Uh-huh.
How's that working out?
So this is, right, the expansion of the universe is, as last year, is only 100 years old. We've known that for 100 years. In my lifetime as an astronomer, we've discovered that expansion is not behaving the way we thought it did for almost a century, right? With the accelerating expansion of the universe, dark energy. And so I would say we are confident in what we see, that the universe is expanding. I think we are still, and those of you who pay attention to cosmology, we are still wrestling around with exactly what it's doing. Right? So let me tell you this last story, and then we'll call it an evening. One of the missions for Hubble was to measure the Hubble parameter, the constant that at the base level tells us what the expansion of the universe was. When I started in graduate school, before Hubble flew, there were two camps of people who thought the Hubble constant was 60, and people who thought the Hubble constant was 100. Hubble flew, we measured the Hubble constant, it was 74 for a bazillion years, and we thought we were done. And in the last couple of years, we're back to, there's two different kinds of measurements that give us different values for the Hubble constant, which is an indicator that, yeah, we know the universe is expanding, but we're not quite sure exactly what's going on. So this is the forefront of cosmology still. What's the expansion and why, and how do we measure it, and how do we confidently measure it in multiple ways to get the same answer both ways, right? That's still what we do. And if you're bored doing whatever you want to do and go back to graduate school, there's plenty for you. So, okay, I'll hand it back to Jim.
Let's thank Sean. Thanks a lot, folks. I wonder if yours is making all this black.
Yeah, I don't know what it was.
Black hole sounds. Sean and I walked over to Sister's Saloon, and I said, it was sunny. Well, of course it was sunny. Don't you need a cap? And he said, oh, no, he didn't need a cap. Well, he gets a cap. You know, we're a small town, and our Ace Hardware is the first place we go when we really need something. And then we usually go back because we got the wrong thing, and a couple times. And so I went back there to return one item, which I bought two, a piece of plumbing, and I gave it to her the receipt, and she said, "This is from Weimar." Oh, I had the wrong receipt. So no, the faucet you're bringing is from Weimar. But who gets those? Some guy there was getting a cap. I said, "Oh, good customers." And I said, well, am I a good enough customer? I returned something to the wrong side. Anyway, she gave me.
Thank you.
So that's got Sister's Hardware, right?
I'll put a Sister's Astronomy Club pin on it.
So we have let's see, something else in here?
Jim's got the whole bag over there.
Just a second. Oh, my organization is not my forte. Well, let me pretend I found it. And pretend I handed it to you. I think it's actually in here.
This is awesome, Jim. What is it? Oh, it's dark matter. I always wanted it.
Here it is. Plain white envelope. You don't have to open it up here. We're very thankful for Bob Grossfeld and his company, Cascades Astronomy and Rocketry Academy.
Nice.
Bob has generously given Shane a gift certificate. So we want to thank Bob for that. Now, I brought this up. Those of you know what a big month this was. We had a great 4th of July thing across the street in Village Green. We had the We had the Sisters Outdoor Quilt Show, which is the biggest outdoor quilt show in the world, by the way. And which I am proud to say, my daughter was the artist who created the art that was on this. We're using the posters as well. And so I said, boy, that's really nice. Why don't we take part of that and make it? She does fused glass art. You can buy it over at Making It Local, I think is the name of the store over on Cascade. Good. Oh, Cascade. Cascade, yeah. So she put this together, and if you look at this art on there, you'll see how. Hold that. Let's get our picture. So we have a night sky, a night flying animal, and some mountains. The art she does is quite beautiful. We're quite proud of it.
This is your daughter?
Yes, my daughter.
Okay.
And her business is called Silly Dog Art Glass, and she sells this products over at, as I said, Making It Local. And so I'll put in a plug for them, for her. And those of you who got time, you can go up to the table there, the Astronomy Club table. If you didn't get a sticker yet, there's Astronomy Club stickers. Some of the best stickers. I had one in my car for almost 10 years on the outside window, and perfectly good. Didn't fade at all. There's some flyers, and there's also cards that tell you about the art, the product, the process of making these pieces of art. And little cards, and there's a little stand there that we're going to put that on for the direct till you leave. We'll pack it up. Okay? So thank you all again.
Thank you all.